Welcome to Lecture 13, whose subject is gravity, one of the fundamental forces of nature. I've chosen to put gravity at this point in the course, and I put it at this point in my textbooks and my college courses also, because I want to build on the ideas of energy we've been developing in the lectures preceding this one. Let me begin talking about gravity, though, with a brief history, and I'm going to make it very brief because there's plenty of history of science in others of the great courses. So let's be quick. We'll run through this quickly. The early views of gravity weren't really about gravity at all. They were about the structure of the universe. And views by Aristotle, for example, and Ptolemy in the years before the Common Era, those views dominated for thousands of years and gave us this picture of a geocentric universe, a universe in which the Earth was at the center. So here's a picture of the universe according to Aristotle and Ptolemy. The Earth is at the center, the Sun is going around the Earth, so are all the other planets. The problem is the planetary orbits are such that that isn't a really accurate description of what goes on. And so the ancient Greeks modified their picture by adding these little circles upon circles. Circles were the perfect kind of motion, so circles are what had to happen up there in the heavens. And so there were circles upon circles that were called epicycles, and they made for a more complicated picture, but it was still basically geocentric, Earth-centered. Now, along came Copernicus, name you all know, he was born in 1473, lived till 1543. By the way, the newest element, Copernicium-112, the newest named element, is named after Copernicus. And Copernicus, of course, introduced the idea of the heliocentric universe. He circulated his ideas before the 1543 publication of his work, but he didn't dare publish it at that point. He still persisted in the idea that all orbits had to be circular because the heavens were perfect and that's where the heavenly bodies were and they had to move in perfect paths. But he put the sun at the center. The Earth is one of the planets going around the sun, and other planets are going around the sun also. And he could get away with smaller deviations from this perfect circularness, and he did that by adding small circles upon circles also. So there's the universe according to Copernicus in his publication of 1543. Well, we move right along. Tycho Brahe, an astronomer, and his student or his assistant Kepler, who carried on after Tycho's death, he used Tycho's very accurate measurements, particularly of the orbit of the planet Mars, to figure out that Kepler determined that the orbits of the planets were in fact not circles, they were ellipses. And this picture is highly exaggerated because the planetary orbits are very nearly but not exactly circular. And an ellipse is a special curve with 2 points called foci. They're like the centers of a circle, but they've been spread out into 2 points. And the sun is at one focus. And Kepler studied these orbits and came up with a number of laws that described not only the fact that they were elliptical and the sun was at one focus, but he talked about how fast the planets moved. They moved more rapidly near the sun, more slowly when they were further out. And he developed relationships between the period and the size of the orbit. He developed what were called Kepler's laws that described the planetary orbits quite accurately, but didn't explain why they were that way. So this is Kepler in about 1610. Along comes Galileo, who was born in 1564, and he was the first to train a telescope on the heavens and really report observations. And he made a number of observations that supported both the Copernican and Keplerian view that the Earth was not at the center of the universe. For example, Galileo observed the moons of Jupiter. The 4 brightest moons of Jupiter are now called the Galilean satellites. You can see them with binoculars, and they constitute a kind of miniature planetary system, Galileo realized, just like what Copernicus said our solar system was like. In this one, you can see the moons going around from night to night. Their positions are different in the sky. Galileo noted that Venus has phases. It goes through a crescent phase where it is relatively large, and you just see a thin sliver of it, and it has a bright full phase where it's much smaller. And he realized that was easily explained by the fact that Venus was going around the sun, and so was the Earth. And so we see phases of Venus in much the same way we see phases of the moon. And finally, Galileo noticed that the sun was an imperfect body. It had sunspots on it. Maybe it wasn't so heavenly and perfect as all that. And so I've titled this slide, Bringing the Heavens to Earth, because Galileo has come close to realizing that what's going on here on Earth and what's going on up in the heavens is not a different realm of physical reality. It's all the same thing, and similar considerations apply. So that's a quick history. He's gotten us through Galileo. And then, of course, we move on to the towering genius of that period, Isaac Newton. In 1665, Newton got his Cambridge degree. He didn't get honors, by the way. Right after that, the university was shut down for 2 years because of the plague, and Newton returned to his home in Woolsthorpe, where he laid the foundations for calculus and his study of optics and gravity. Now, I want to point out, before I talk about Newton's, quote, discovery of gravity, that it didn't take Newton's genius to discover gravity. Our cave ancestors had to understand gravity, or they wouldn't have survived. They would have fallen out of the trees. They would have sat under their cave and a rock would have clunked them on the head. And then they would have woken up, gee, there is gravity. They knew about gravity. What was different about Newton was the extension of gravity from what we recognized on Earth to a force that operated throughout the whole universe. And I want to spend the rest of the lecture on that, on Newton's discovery and Newton's formulation of a law of gravity. So here's a kind of cartoon that may or may not represent the truth, but here's Newton sitting under the apple tree, and rumor has it the apple fell, clonked him on the head, and he realized gravity. Well, that's the point I'm saying. That's nonsense. Our cave ancestors knew that. If this picture is true, Newton was looking at the same time at the moon. And what he recognized and what his genius was to realize that the same force that keeps the moon in its orbit is the same force that pulls the apple down from the tree and clunks him on the head. Those are one and the same force. Newton called them universal gravitation, and he developed a formula that describes the universal gravitation not only between the Earth and the moon and the Earth and the apple, but also the sun and the Earth and the sun and the other planets, and indeed between any two masses in the universe. So here is Newton's universal gravitation. In fact, you saw Newton's universal gravitation back in Lecture 2 when I talked about how I was going to use mathematics in this course and how I was going to give you anatomies of important equations. So let's look at an anatomy of universal gravitation. So what we see here is a picture of, in one case, the Earth on the left, the moon on the right. They are exerting forces on each other. Those forces are vectors, so I've got the arrow over the F, and I've got the big arrows representing the vector forces. They are a distance r apart, center to center. And that center to center is important. It turns out, although Newton had to show this, that a spherical mass acts as if it were a single point located right at its center. And so this r is importantly the center to center distance when we talk about gravity. So there it is. And Newton came up with this formula. He said, I think the force of gravity is proportional to the two masses and inversely proportional to the distance between them. The force F is the force between two masses m1 and m2. The two masses m1 and m2 are there. That's the square of the center distance between the masses, and there is some constant of universal gravitation. Newton didn't know its value, by the way. It was not until 1797 that Cavendish measured its value, and he had to do so by actually measuring the gravitational attraction between two laboratory-sized masses, a very difficult and delicate thing to measure because the gravitational force between everyday-sized masses is really very, very weak. By the way, you'll notice that Newton's universal gravitation also obeys Newton's third law. You can see that I've drawn the two force vectors the same length, and you can see in this equation it doesn't matter whether it's mass 1 or mass 2 that comes first. The force of mass 1 on mass m2 is equal to the force of mass 2 on mass m1. So we have universal gravitation. Universal gravitation acts between any two masses in the universe. It keeps the sun and the whole solar system pulled toward the center of the galaxy. It doesn't move toward the center of the galaxy for reasons we saw in Lecture 6, but it goes in a circular orbit around the center of the galaxy. Every pair of masses in the universe attracts every other pair of masses with a force that is inversely proportional to the square of the distance between them. By the way, Newton, although he didn't know the value of g, was able to verify his 1 over r squared fall-off by looking at the moon, considering the acceleration of the moon. He knew the period of the moon's orbit. He knew the radius of the moon's orbit. He could calculate the acceleration of the moon in its circular path using the considerations we developed in Lecture 6 on circular motion. And he compared that with the acceleration of the apple or some other object falling near Earth, 9.8 meters per second squared, and he found that the moon's acceleration was smaller by exactly the factor 1 over the square of the ratio of the distance between the Earth's center and the moon and the Earth's center and the Earth's surface. So he was able to verify this inverse square relationship. But the big thing that Newton did was to show that his formula for universal gravitation said that the planets should move in orbits exactly as Kepler had described. The sun should be at one focus. They should move faster, closer to the sun. There was a period-size relationship. The planetary orbits are close to circular. He doesn't show this with his equations, but that, in fact, is the case, although there are things like comets that go in highly elliptical orbits, and Newton showed that all these bodies moving around the sun would obey Kepler's laws. Now, that is not as easy as it sounds. I can't just give that to you as a challenge. And for Newton, it was a particularly big challenge because the branch of mathematics that deals with that kind of continually changing situation. Circular orbits are easy, but elliptical orbits, complicated. The distance is always changing. The force is changing. Complicated. Newton didn't have the mathematics to solve that, so he invented the mathematics, and that was calculus, and he used the calculus to show that his equation of universal gravitation led to orbits that were just like Kepler described the planetary orbits as being. So that is a big step. And Newton had another realization. He realized there was the possibility that we, human beings, could possibly put things into orbit. We could launch satellites. And he realized the possibility of satellite orbits. And here's how he did it. He imagined planet Earth with a giant mountain on top of it. And we have to also ignore the presence of the atmosphere or let the mountain stick up above the atmosphere. Or, in modern terminology, we might launch a rocket straight up to that altitude, tip the rocket sideways, and fire its rocket again. Here's Newton's realization. You stand on this high mountain, and you throw something off it horizontally. If you throw it with modest speed, it's going to go a ways, and it's going to describe a path that ends up intersecting the surface of the Earth, and the object crashes to the ground. And from earlier considerations when we talked about motion under the influence of gravity, you might say, well, that path is a parabola. But that was on the assumption that the Earth was flat. We neglected the curvature of the Earth. Here, that path is, in fact, part of an ellipse. It's just an unfortunate ellipse because it intersects the surface of the Earth. Throw the object a little faster, and it goes around a little more before it hits the ground. Throw it faster still, and the ground curves away from it at exactly the same rate at which gravity is pulling it out of the straight line path that it would otherwise go in the absence of any force acting on it. Remember Newton's first law. An object moves in a straight line at constant speed unless there's a force acting on it. Second law tells you how much that force changes its motion. What keeps a satellite up? That's the wrong question. As I talked about when I described forces and the influence of forces, here's an example, an analogy with a satellite. This is a ball whirling around on a string. It's perfectly analogous to a satellite or the moon in its orbit around the Earth or a planet in its orbit around the sun. What's going on here is there is a force. The force is acting toward the center of the circle. The force is pulling that ball out of the straight line path it would otherwise go in. It's not a question of why doesn't it fall toward my hand. There is a force on it pulling toward my hand. But forces don't cause motion. Forces cause changes in motion. So the question, why doesn't the satellite fall down, is really the wrong question to ask. The right question is simply this. Is the satellite's motion being altered from the straight line it would go in the absence of any forces? And is that alteration such that the force is equal to the mass times the acceleration? And for just the right speed of launching that satellite off that mountain, the answer is yes, we will get a circular orbit with the circular acceleration. If the speed is a little slower, we'll get an elliptical orbit that may or may not intersect the Earth. And if the speed is a little bit greater, we will get an elliptical orbit that climbs to a higher point than the mountain, and the object is moving slower as a result, and then comes around and turns back. So that is Newton's profound realization about the possibility of artificial satellites. Let's do a modern-day example of that. Let's talk about a special kind of orbit, which is in fact the most valuable piece of real estate in space. It's called geosynchronous orbit, and it's the orbit where a spacecraft would circle the Earth once in 24 hours. And what that means is if you put a spacecraft at that correct orbital altitude and give it that correct speed and put it above the equator, so it's going in an orbit that's in the plane of the Earth's equator, it will appear to hang motionless in the sky. And you can imagine how valuable that is. That's where you put communication satellites. That's where you put the satellites that are giving you your TV, satellite TV and satellite radio, and where you're bouncing radio signals and telephone messages and all kinds of stuff around the planet. Geosynchronous orbit is a very valuable place in the real estate of space. So let's find out where geosynchronous orbit is. Low Earth orbit, satellites that are a few hundred miles, a few hundred kilometers up where we put the International Space Station, they take about 90 minutes to go around. The moon orbits in 27 days. So somewhere in between there's an orbit of 24 hours. That's geosynchronous orbit. Where is it? Well, we know from Lecture 6 that the acceleration of an object in a circular path is the square of its speed divided by the radius. Speed is distance per time. For a circular orbit, that's the circumference, 2 pi r over the period t. So I'm going to write v as 2 pi r over t. So a, the acceleration, is v squared over r. That becomes 4 pi squared r squared, but then divided by r. So there's just one r upstairs, and there's our t squared downstairs when we square that. So that's the acceleration. So we're still asking the question, where is this geosynchronous orbit? We now know the acceleration. It's 4 pi squared r over t squared. Newton's second law, which governs motion, tells us that the force is equal to the mass times the acceleration. We know the acceleration. We also know the force, because the force is Newton's force of universal gravitation, where one mass, little m, is the mass of the satellite, another mass, big M, is the mass of the Earth. We're looking for that distance r. We know g, we know everything else in here. Let's do it. So I'm going to equate those two. That's the statement of Newton's second law. The force is the mass times the acceleration. There's the mass, there's the acceleration, there's the force. The little m cancels, which is nice, because we don't have to say, oh, let's put a satellite of 25 kilograms in this orbit. We've got to have a different geosynchronous orbit for a different mass. No. As usual with gravity, mass cancels out because all things experience the same gravitational acceleration. Solve that. We get the cube root. By the way, that cube root and the squared in there is Kepler's period orbital size relationship. Work out the details. There's the orbit radius. Do the numbers. There's the period. We want the period to be 24 hours. There's the mass of the Earth. There's the gravitational constant. We get 42,000 kilometers. That's from the Earth's center, because the center-to-center distance is what counts. We subtract Earth's radius of about 6,300 kilometers, and we get a geosynchronous altitude of 36,000 kilometers, about 22,000 miles. That is the most valuable piece of real estate, at least in near-Earth space. We have many, many satellites up there. In fact, so many that we're getting worried that their beams will begin to interfere with each other. Okay, well, let's move on. I indicated I was putting this lecture here because of energy considerations. Let's move on and look at energy in gravitational situations. We found earlier that if we had a mass m and we lifted it through a height h, the change in its gravitational potential energy was mgh, and we've used that a lot. We can't use that anymore because now we're dealing with going large distances from Earth, and the strength of gravity is falling off substantially if we move distances that are significant compared, for instance, to Earth's radius. So let's look at gravitational energy. Let's take a look here on the big screen because we want to do a little bit of mathematics with this. Okay, back in Lecture 11, we found that potential energy is the area under the force versus distance curve. Here we have the force of gravity. It's this force that falls off as the inverse square of distance. It's an attractive force, and that means as I move an object closer to a gravitating mass like the Earth, work is done on it. I do negative work, and the potential energy associated is negative, and it's this area under the curve. And as I move close to the gravitating object, a substantial amount of potential energy is involved. As I am moving in regions further away, because the force is falling off so rapidly, less potential energy is involved. And I'm going to cut to the chase. Here's what calculus, which again Newton invented to do this kind of thing, shows. Newton's calculus shows that if you take zero potential energy to be way off at infinity, and then you bring an object closer to a gravitating center, like start with an object very far from Earth and bring it closer to Earth, the potential energy goes down, meaning that it would take work to move that object farther away from Earth. So potential energies, gravitational potential energies, are negative, and the calculus shows that you get a gravitational potential energy that depends inversely on r, whereas the force depended inversely on r squared. Same gravitational constant, mass of the object doing the gravitating and mass of the object moving near it. It doesn't really matter which is which. So that is the gravitational potential energy. And let's take a closer look at that equation. An anatomy of that equation, U is the gravitational potential energy associated with two masses, big M and little m, a distance r apart. Zero of gravitational energy is at infinity when they're very far apart. There are the two masses. There's the distance between center to center of the masses. There's the constant of universal gravitation. And that minus sign tells us that the gravitational potential energy is negative, and we're therefore dealing with an attractive force. It would take work to separate two objects that are connected gravitationally, that are undergoing this attractive gravitational interaction. Okay, let's do some practical things with this equation. Let's ask now about the total energy of an object that is in the vicinity of a gravitating center. It may be moving. It probably is moving. If it's not moving, it's going to start moving because gravity is going to pull it downward. So it's going to have kinetic energy and it's going to have potential energy. The kinetic energy, we know, of a mass m moving at speed v is a half mv squared. We've just seen that the gravitational potential energy of an object a distance r from a mass capital M, the same object, mass little m, is minus gmm over r. So that is the total energy, kinetic plus potential, of an object moving in the vicinity of a large mass m that's exerting a gravitational force on it. And what I'd like to do is use this to calculate a very special situation. I'm going to leave that on the screen for now so we can refer to it. And let's look at a situation in which I take this tennis ball and I throw it up in the air, and of course it comes down. What goes up must come down. And I throw it a little higher, and it goes a little higher before it comes down. And I throw it higher still, and it disappears out of your picture, but it still comes down. Could I throw it fast enough? Could I throw it hard enough that it would leave the vicinity of Earth and travel to infinitely great distances from Earth and never come back? Must what goes up come down? That's the question I want to ask. And I'm going to answer that question by looking at gravitational potential energy and kinetic energy and their relationship in the total energy. So let's take this equation that we've just examined for the total energy and let us see what happens if we ask that question about throwing a ball up and must it come down. So what goes up must come down? Question mark. Let's launch a mass m from Earth's surface. The question is, could we get it infinitely far away without having to throw it at infinite speed? Let's apply conservation of energy. Potential energy approaches zero at large r because we defined the zero of potential energy when two objects are infinitely far apart. If it just barely gets to infinitely far from Earth, then it's going to be going slower and slower and slower because gravity is always going to be pulling back on it. And it's going to reach infinity, and this is sort of a story where you have to stretch your imagination a little bit because this is going to take forever. It's going to reach infinity just barely coming to a stop. Now, if you don't like that, throw it a little faster. It'll get all the way to infinitely far away. It'll still take infinitely long, and it'll still be coasting a little bit. But that dividing line is the case where the kinetic energy is also getting to zero at large r. So both those terms in our equation for the total energy are zero, and therefore the total energy adds up to zero for the case where I just can get the object infinitely far from Earth. Throw it a little faster, and it'll get to infinity with a little bit of energy to spare. Throw it a little slower. It may go light years away, but in principle, in a universe containing only the Earth where it doesn't get captured by something else, it will come back to Earth eventually. So there's this dividing energy, and it will correspond to a dividing speed. So if we express this at Earth's surface, zero, the total energy, the sum of the kinetic energy and the potential energy, at Earth's surface, the potential energy is negative. We're close to Earth. The kinetic energy is the energy I need to give it to throw it away. And when it gets infinitely far away, both of those terms are going to go to zero. They're zero at the surface. Not both of them, but they add up to zero at the surface. So let's find out. That implies if I solve for the unknown speed is the square root of 2gm, mass of Earth, over the radius of the Earth. As usual with gravitational problems, the mass is canceled. It doesn't matter what mass we're throwing. So the answer to this question, what speed do I need to throw something at to get it infinitely far from Earth, doesn't depend on the mass of the thing I'm throwing. Do the numbers. For Earth, you get 11 kilometers per second, which is about 7 miles a second. That, by the way, is a speed achievable with our rockets. We have spacecraft to the outer planets that have left Earth with more than this speed. This is called the escape speed. We even have spacecraft, the Voyager and Pioneer spacecraft, have escape speed relative to the sun, so they can escape the sun's gravity, and they will travel through the galaxy basically forever until they crash into something or extragalactics pick them up or whatever. Escape speed. Anticipating what's going to come in the very final section of the course when we talk about ideas of modern and contemporary physics and general relativity in particular, we'll ask what would have to happen for escape speed to be the speed of light, and we'll be able to derive that quite simply using these considerations, and that's what creates a thing called a black hole, because nothing can escape from the black hole, because nothing, as we'll see, can go faster than light. So what goes up must come down, question mark? The answer is no. If it leaves with more than escape speed, it's not going to come down again. It's going to escape forever. So zero total energy, sum of kinetic and potential energy being negative as long as you're not infinitely far away, that sum being zero is a dividing line between situations in which you're bound to a gravitating object like the Earth and you can't escape it forever, and situations in which you are not bound to it, and even though you might be near it at some point, you will eventually get infinitely far away. So what goes up must not necessarily come down. Okay, let's look in a little bit more detail at what that means. So we have E less than zero is one possibility. If the total energy of the object is less than zero, it's in a closed orbit, and the orbit will be in general elliptical, although the circle is a special case of the elliptical orbit. If the energy is exactly zero, we'll be in a borderline case where there's just enough energy to escape, and it turns out the orbit then is parabolic in shape. If the energy is greater than zero, it's in an open orbit, it has enough energy to get to infinity with energy to spare. The orbit is hyperbolic. It might come in from very far away with a high speed. Here's a gravitating object like the Earth, and it kind of gets bent, its path bent a little bit, but then it goes off and eventually on a straight line path very far away with plenty of energy to spare, and it's not bound to the Earth. So those are the orbits and the energies and the considerations of what kind of orbit we get with different amounts of energy. Okay, as we end up, let me issue you a challenge. Normally I like to put challenge problems at the very end and let you do them or not. But this challenge problem you don't have to do because it's a show something problem. If you would like to, derive an expression for the total energy E in the case when we're in a circular orbit, and show it can be written entirely in terms of either the kinetic energy K or potential energy U. You can stop now if you want and work that out. Here's the answer. It turns out that the total energy is negative, because the object is bound if it's in a circular orbit, and it turns out to be exactly half the potential energy, and it's exactly minus the kinetic energy being positive. Again, you can work that out by understanding what you know about circular motion and the forces in circular motion and the energy and the velocity and so on. You can get to that result. So there's your challenge. And I want to take the result of that challenge and describe an important and rather counterintuitive aspect of how we move spacecraft around in their orbits. Because look at what this says. Kinetic energy is related to speed. If I make the kinetic energy bigger, and again, this applies only to circular orbits. It's relatively easy to do the math of this consideration for circular orbits. If I make the kinetic energy bigger, because the total energy is minus the kinetic energy, the total energy actually goes down. So very strange, very counterintuitive. Make the object go faster. That is, make it go into a circular orbit where it's going faster, and the total energy has to go down. That means that faster circular orbit is a lower circular orbit. It's got even lower negative potential energy. And so what that means is, if we want to maneuver a spacecraft using this equation, we have to slow down to speed up. So here I have a spacecraft that wants to catch up with a space station. You'd think, well, it just blasts its rockets and goes faster. But if it blasts its rockets, the first thing that will happen is it will rise into a higher orbit, and gravity will sap its kinetic energy, and it will actually end up going slower. So what we have to do is fire our rockets in the opposite direction, as if we wanted to slow down. We would drop into a lower orbit. We travel faster in that lower orbit, and when we come abreast of the space station we're trying to meet up with, we fire the rockets the other way, this time in the forward direction, and that brings us to a higher but slower orbit. So orbital maneuvers are definitely very, very counterintuitive. Okay, well, let's wrap up with a summary here. We found that the gravitational force acts between any two masses The force is proportional to the product of the masses, inversely proportional to the square of the distance between them. This gives rise, through Newton's calculus, to circular or elliptical orbits, at least in the case of bound systems with total energy negative. There is a gravitational potential energy, which is negative because we're taking the energy to be zero at infinity, and that indicates if you're closer in to a system, you could be bound to it if your total energy remains less than zero. Total energy being the sum of your kinetic energy and your gravitational potential energy. If that's less than zero, you're in a bound orbit. If it's greater than zero, you're in an open orbit and will never return. And the dividing line defines a special speed, the escape speed, at which you would have to launch something from a gravitating object for it to be able to escape that object forever.